Students, hi, this is Mr. Bob, and in this video, we're going to talk about applying Kirchhoff's laws to solve problems. This is subtopic 5.2. Before watching this video, remember, you should have already watched the two previous videos, the Bozeman science videos about the Kirchhoff's junction rule and the Kirchhoff's loop rule. Make sure you have focus notes set up and make sure you have at least two different colors, pens or pencils or highlighters. And then I strongly recommend after watching this video about 2 to 4 days later, you could read the section of the Jane Coley textbook that I'm listing there, and also you could revisit your notes in a way that makes your brain think. In other words, fill in, add group, add questions to the left, and also point out or identify points of confusion. The other thing I want to say is just remember, these are always true. Please avoid mindlessly copying, stop and rewind the video as needed. Only selectively write certain things down, right? You don't necessarily need to write down everything, abbreviate. For the sample problems, pause them and try and solve them yourself and get as far as you can before you continue with the video. Make your brain struggle. And again, as always, if you have a point of confusion, please reach out to me or a classmate or revisit the notes a few days later. So the essential question is, how can we apply Kirchhoff's laws to analyze complex circuits? And that's a picture of Gustav Kirchhoff, the physicist who came up with this, otherwise known as Snoop Dogg Kirchhoff. So before we actually get into a sample problem, I just want to make sure we understand how the convention needs to work when we're talking about Kirchhoff's loop rule, okay? And we're talking about the loop rule. Remember, we're talking about starting at one point in the circuit. Let's say this was our circuit here. And we're saying we're going to go all the way out around any given loop in the circuit. And what Kirchhoff's rule says is basically, regardless of the loop I choose, I could choose that loop, I could choose this loop, I could also choose a third loop in this case. I'll do that in blue here. I could start here. Regardless of what loop I choose and what direction I go, when I make a complete loop around a circuit, the potential difference, the sum of all the potential differences that I encounter along the way has to equal 0. And this is really an expression of the law of conservation of energy. Okay, so there are certain conventions we have to follow so that we can appropriately apply this rule. And here's what they are. So let's say I define the purple loop, and I define in the purple loop that I'm going from left to right. And let's also say that in this circuit, I've defined that current I1 is going from left to right, okay? So notice here I have the current going from left to right, and I'm also traveling around the loop, applying the loop rule from left to right. If that's the case, if the direction I'm traveling and the current are traveling in the same direction as I pass through a resistor, then the voltage drop is going to be negative. And let's just remember Kirchhoff's law here, where we get this from, or not Kirchhoff's law, excuse me, Ohm's law. The current traveling through any sort of device in a circuit is equal to the potential difference across that circuit element divided by the resistance offered by that circuit element. So if I want to find the potential difference, right, that's just going to be current times resistance. So in this case, if I was going this direction, this would be a negative I1 times R2 in this example. If I had defined the loop that we're talking about here, the other direction, okay? In other words, if I was going around in this case counterclockwise, okay, then I would be moving in the opposite direction that the current was traveling. And then this would mean that it's a voltage rise as I travel applying Kirchhoff's law. So in this case, this would be a positive I1 times R2. Okay, this will make more sense when we get to a sample problem. When we talk about batteries, first thing I want you to know is IB often uses the word cell. And when they say a battery cell, or they just say a cell in a circuit, they're talking about a battery, okay? If our loop goes through a battery from a negative to the positive terminal, then the energy change or the potential difference is positive. So in other words, remember, this is negative, the shorter end is negative, the larger end is positive. This is going to be a voltage gain as I'm applying Kirchhoff's loop rule. If I'm traveling the opposite direction, if I'm traveling in that direction around a loop and I encounter a battery and I'm going from positive to negative terminal, that is a voltage drop, okay? And it has to be expressed as such in the equation. All right, let's get into the sample problem. Notice we have this pretty tricky looking circuit here. We've got 3 batteries, 4 resistors, 3 different current values. What the heck, how are we going to solve this? Well, we're going to apply Kirchhoff's laws and it's going to be awesome. So first thing it asks is to apply Kirchhoff's junction law to this red dot up here, okay? So remember, Kirchhoff's junction law says what? The sum of the currents going into a junction has to equal the sum of the currents exiting the junction. This is just simply an expression of the law of conservation of charge. So what are the goes-ins, so to speak, for this junction? Notice going into this junction, I have I1, and I also have the current I2 plus I2. What's the goes-outs? The only goes-out current is this one, the I3. So when we apply Kirchhoff's junction law, we can basically say for that junction, I1 plus I2 equals I3. And that's an important equation that we're going to keep with us as we move to the next slide. So I'm going to copy it down on the next slide here. Let's go. So number one, I1 plus I2 equals I3. Okay. The next thing it says is apply Kirchhoff's loop law to the left side. And I'm going to use purple for this. And I'm going to define, and by the way, it doesn't matter whether you go clockwise or counterclockwise. It should work either way, but I'm just going to define the loop as being clockwise in this case. And I'm going to start at this lower left corner. I often like to start in the negative terminal of a battery. It's just a personal preference. So let's apply Kirchhoff's loop law to this left side loop. So that means, remember, the potential difference across the entire loop has to equal 0, okay? Or the sum of the potential differences across each of the resistor items, each of the circuit elements. Okay, so the first thing I encounter when I start moving clockwise is I encounter this negative terminal of this battery, and I'm going from negative to positive. So what is that? That is a voltage increase. That would be a positive V1. As I keep going around the circuit in a clockwise fashion like I've chosen to do, I have I1 defined as being from left to right, and I have this 8 ohm resistor. And so I'm moving in the same direction as the current is as it travels through the resistor. So that is a voltage drop by convention. So that would be a minus I1 times the 8 ohms. As I keep going, I'm going to make a turn here, and then I'm going to encounter the positive terminal of V2 and then the negative terminal. So now I'm going backwards through the battery as opposed to the way I went through it through V1. So that would be a negative because it's a voltage drop, so minus V2. And then finally, I'm going through this 2 ohm resistor, but I'm going in the opposite direction that the current has been defined as going through it. So I2 is going from bottom to top, and I'm going from top to bottom. So this is going to be a voltage gain again. So this is going to be plus I2 times 2 ohms. And finally, when I make this turn and come back here, I get back to here. And so I know once I reach back here, all of these added up have to equal 0. Okay? Now I'm actually going to skip to part 4 now because I can start doing that with this equation here. Because if I substitute these values, because look, I'm given certain values here. V1 is 10 volts, right? V2 is 2 volts and I2 is 4 amps. So I can basically solve for this. And in doing so, I'm gonna drop the units just because it just makes it a little easier. 10 minus 8 I1 minus 2, because that's what V2 is, plus 4 times 2 has to equal 0. Awesome. So what do I got here? I have 10 minus 8 I1 plus 6 equals 0. Okay, I can bring the 8 I1 to the other side, and I can, whoops, let's go back here. I can basically get this to be 16 equals 8 I1. You can do it differently than I did it, but you should get the same answer. Eventually you get that I1 equals 2 amps. Okay, so I've solved. I've gotten that I1 equals 2 amps. Now look, now that I know that I1 equals 2 amps, what can I do? I can take this and stick it in here. And knowing that I2 is 4 amps, I can solve for I3. And that's what I'll do here. Let me just do it in a different color to make it stand out a little better. So I'm going to solve for I3. So I1 plus I2 equals I3. We now know that the current 1 is 2 amps, current 2 is 4 amps. So that makes I3 6 amps. Awesome, we're 2/3 of the way there. Okay, so all I need to know now is V3. In order to do that, I'm going to go to the next slide, and I'm going to apply Kirchhoff's loop law to the right side loop. So let's do that. Okay, so Kirchhoff's loop law to the left. So again, it's up to you how you define this. I'm going to define this as being clockwise again. But again, you could get the same answer or a correct answer, which would be the same answer if you defined it the other way. So if I start, let's say I start right here at the top right corner, because again, I like to start where the negative terminal of the battery is. Again, that's just a personal preference. And I start moving this direction. The first thing that happens is I go through that battery V3 from negative to positive. So that's a voltage rise. So delta V loop equals 0. That's Kirchhoff's loop rule. And the first thing I have is positive V3. Turn the corner here, get to this 3 ohm resistor. This current, this I3 current is going like this, and I'm also going with it. So that is going to be a voltage drop, as we talked about. So that is minus I3 times 3 ohms. Okay, make the turn here up this center branch. I got a 2 ohm resistor and I've got I2, and I'm again going in the direction, the same direction as the current. So that's another voltage drop. So that's minus I2 times 2 ohms. Then I get to V2 here. This time I'm going through it from bottom to top. That's negative to positive. So that's a positive V2. Turn the corner here, almost back home, but need to go through the 4 ohm resistor, and I'm going through it left to right, same direction as the current. So that is a minus I3 times 4 ohms. And I'm back to where I started, so all that has to equal 0. Okay, so let me just simplify this a little bit. So that's V3 minus 3I3 minus 2I2 plus V2 minus 4I3 equals 0, okay? And so let me just copy down here. So this was 2 amps and 6 amps. So this is 2 amps, this is 6 amps. So now we're just gonna plug in and we're gonna solve for V3. So I'm just gonna do it this way, V3 minus 3 times 6 minus 2 times 2 plus 2 minus 4 times 6 equals 0. So what do I have here? This is negative, well, I don't know where I paused. So I just want to recap what happened here is I made the loop go clockwise for the right loop, applied Kirchhoff's loop law. And I did make a mistake initially here with 2 amps right here, putting 2 amps in for I2 when it's actually 4 amps. But when I corrected it, basically, and I did the math, it came out to the V3, the battery voltage for battery 3 is 48 volts. So hopefully from this video, you're able to understand and get a better sense of the essential question of how we can apply Kirchhoff's laws to analyze complex circuits. Thanks, everyone. Have a good rest of your day.